Hello students. For Module 3, we begin discussing the derivative. This is one of the three main topics of Calculus 1, along with the limits and the antiderivative. Among the three, this is the most important both in terms of the time we spent and the number of exam problems. Okay, let's begin. Some preparation first. Let's discuss the rate of change, and that begins with the average rate of change. Let's begin with a certain function y equals to f of x, which is represented as a blue curve in this picture. And we define the average rate of change as the change of the function value over the change of the original variable. In terms of graphs, the function value is y-coordinate value, and the original is the x-coordinate. So change of function value over change of original is the change of y-coordinate over change of x-coordinate, delta y over delta x, or rise over run. What is rise over run? It's a slope. And in this case, it's the slope of this green line, which is called the secant line. The secant line is a line that is obtained by cutting through a certain curve at specified starting and ending point. We take the starting and ending point of that interval and then cut through and measure the slope of the secant line, and that is the average rate of change. The rise over run, delta y over delta x. What does it measure? For example, if this blue curve, this y equals to f of x, is about the temperature distribution of certain time frame, then this change of function value is a change of the temperature, and the change of original variable, that's a time span. So this rate is change of change of temperature over change of time. That measures how quickly the temperature is going up or down. It doesn't have to be temperature, of course. If you want to measure how quickly a stock price is going up or down, change this into dollar amount, and that's about it. In any case, this is a rate of change. Now, why is it called average rate of change? That's because we are considering a certain interval a to b. You can obtain the same average rate of change by following this blue curve or some other curve, as long as we are running through these red and green points. So it's called the average rate of change. The computational formula for the average rate of change is this one, f of b minus f of a over b minus a. So frequently we call this one as the average rate of change, even though the concept is closer to this one. What is f of b minus f of a here? The numerator. That's a change of y-coordinate because that's y-coordinate minus this y-coordinate, that's delta y. And the x-coordinate is going from a to b, so that goes down here. So this rate is the same as delta y over delta x, the average rate of change. And this is a computational formula, especially when you have an algebraic expression of the function, not a graph. Now what we're going to do next is the follows. We're going to take the second reference point, the green point, closer and closer and closer to the original red point. And consequently, this secant line will get closer and closer and closer to another line, which will turn out to be a tangent line, and that's what we call the instantaneous rate of change. But please be patient. Please be patient. Before going over to the instantaneous rate of change and the tangent line, let's discuss some algebraic manipulation of this formula. This is what I'm talking about. This quantity is the algebraic formula of the average rate of change. Now here, let's take this change of variable. Let's take denominator h as b minus a, b minus a as h, which means this denominator b minus a will be replaced into this single character h. If I do that, this is equivalent to that. All I have to do is flip this a to the other side. Therefore, this b will become a plus h. In short, this quantity, the computational formula for average rate of change, and this expression are the same. The latter quotient is called either difference quotient or Newton quotient, but in reality they mean the same thing. Here's a visualization. Same graph, Same secant line, same slope, same everything, but only labeled differently. This point is labeled as b comma f of b, just like the previous case, but if I take this change of variable, then b is a plus h and f of a plus h. And what do we get? The difference of y-coordinates is this f of a plus h minus f of a. Consequently, we get this numerator. And what's the difference of x-coordinates? A plus h minus a, that's h. So this expression and that expression may look different, but graphically they are the same. And of course, in terms of average rate of change, they mean the same thing. So here's the conclusion. Average rate of change, rise over run, or delta y of delta x, or f of b minus f of a over b minus a, the average rate of change formula, or f of a plus h minus f of a over h, Newton quotient. They all mean the same thing, and they all mean the slope of secant line. Okay, now are we ready to move on to the instantaneous rate of change? Let's go ahead and do that. All three are equivalent. We'll take the limit. From the Newton quotient, simply take h is going down to 0, denominator is going to 0, or the average rate of change formula, b is going to a, so again the denominator is going to 0, or this rise over run, delta y over delta x, well, denominator is going to 0 again, and that thing is called the instantaneous rate of change if the limit exists. This is basically a 0 over 0 type limit, and the final expression is by Leibniz. And instead of this delta y and delta x, which represent the difference, he changed those deltas into Roman d to represent infinitesimal difference. So this is basically 0 over 0, or a little bit more precisely speaking, infinitesimal over infinitesimal. Graphically speaking, it's this. All these expressions represent slope of secant lines, and we have a bunch of slope of secant lines here, as you can see, and all these secant lines are converging to this red tangent line. You can clearly see that, and here's an animation, a dynamic view. You can see the convergence, alternatively like this. Okay, so much for the rate of change. Three different expressions, three different but equivalent expressions of average rate of change. Computational formula for the average rate of change, Newton quotient, and the limits. We discussed all those. Now, let's go over to the definition of the derivative, and that's where we're going to stop. What is this? This is average rate of change, and upon taking the limit, what do we get? We get the instantaneous rate of change, and that's what we call the derivative, f prime of a. Equivalence definition is here. Instead of this practical formula for average rate of change, we change it into Newton quotient because they're equivalent, and then denominator going to 0, where we have instantaneous rate of change. This quantity, again, we called the derivative. The instantaneous rate of change is called the derivative. Here's still equivalent expression, by the way. I clicked the wrong key, sorry about that. And delta y of delta x, rise over run, and we take the infinitesimal over infinitesimal, we get the final expression. There's a bit of a history behind all these. This is called Newton quotient and all, especially this one, this part. This is called Newton quotient, and that's by Isaac Newton, and that's British approach. And then this notation here, f prime of a, the prime notation is by Lagrange. I thought Lagrange was French, but he studied and worked in France, but he's actually Italian, born in Italia. And then this expression, delta y delta x, leading it to this dy dx, that's by Leibniz, that's German. And finally, the limit concept is by Cauchy, it's by France. So we are talking about a collaboration of various different cultures, and consequently we have different expressions. Has been going on like that for 100 years in different parts of the world with rich history of their own. And what choice do we have? We have to accept all of them. It's too late to go back in time and change all those into whatever we are liking. We don't have any choice. We have to get through with this expression or that expression or this expression which is students' favorite or that expression. We have to study them all.